9 out of 10 times I use NAT, only NAT. Because mostly when I run a virtual machine, it's to run Windows. And by running that NAT, I'm one layer away from somebody being able to violate my machine. The other thing is that your host machine's firewall will protect your guest machine. So under Mac or under Linux, which have firewalls built into them, I guess Windows 7 now has a decent one built in too. Well, it has one, let's not put decent on there, it has one. The firewall that comes with your operating system will protect you through this NAT connection rather than the Briggs, which will put you in front of the firewall. Okay, so just be careful with what you're doing there. It's always safe to leave it under NAT unless you want to be a server. USB controller, I have never touched the USB controller, it just always works, and I'm happy that it works. And there's not a whole lot of stuff in here. Sound card, same thing, if you want to listen to sound. Printers is something new, and they keep changing things between versions. So the Workstation 5 had printer support over a serial port. So if you plug the printer into your PC serial port, you can print to it. Kind of lame. Version 6, they let you print to your printer over a virtual parallel port, but it kind of worked, and then sometimes it didn't kind of work. And now with version 7, what they're doing is they're going to pretend that you have a whole bunch of printers connected to your USB bus, and they're going to happen to be the same printers that your host operating system has. But they're all going to have the VMware driver. So you'll see like a printer named Hewlett-Packard LaserJet 5000 that has the VMware print driver to it. And what that's going to do is it's going to let Windows or Linux print to whatever printer and have it go out to whatever printer you're talking to. And they'll do the translation between what the VMware printer sees and what your other printer sees, because they all talk a different language. So VMware is going to try to virtualize that. Sometimes it works out well, sometimes it doesn't. Mileage may vary. And then display. Version 6 and then version 7 have this kind of interesting idea that you might want to play games under VMware. And so they're going to try to accelerate your graphics so you can play games under VMware. It's a nice idea, but not so much. I've never seen anybody try to play a real game under VMware and have it work.
Yeah, it's not very efficient.
Yes, absolutely.
Is it like a real 3D shooter, moving around graphic kind of game?
Civ.
Okay, it's on the older side. Yeah, it's not. Like I was able to play. What was that? What was it? What was the game that Dudley and I you were playing that one time? Age of Empires. That works. And that's kind of graphic intensive, but it's not like Halo or something crazy like that. Nothing major. So don't think you're going to be able to really get 80 frames per second with this, but it'll work a little bit.
Be more crisis.
Yeah, not All right, so we've made our changes. 2 gigs of RAM, 2 processors, a bunch of stuff, and now the new VMware does something really slick. It knows most of the common operating systems, and it knows that I'm installing Ubuntu. And so at this point now, it's going to start installing Ubuntu, and it's going to answer yes and no and continue and I agree at all the right points and type in the password and the user ID and all the stuff that I told it to, and it's going to end up with a fully installed Ubuntu installation when it's all done. So it's all kind of automatic now. It's kind of slick. It will do the same thing for Windows XP and Windows 7. So if you put a Windows XP ISO on it, or say go install, it'll ask you a couple of questions like your username, your password, what your product key is. It'll run for half an hour, so you can go get a coffee at Starbucks and come back, and you'll have a virtual machine all installed and ready to go. So they've done some nice trickery here. So while this is going on, anybody know how they pull this really cool feat off? How does this stuff work? Because that's really kind of interesting. It's all magic, right? They have a bunch of gremlins in there that just kind of read instructions, and all this kind of magic comes out. How does your operating system and your user applications, how do they communicate with each other? Like when I want to talk to the hard drive and I want to read a file, how does that happen? Someone has had to have operating systems to know the answer to that. The user applications just get to read the hard drive directly? Yes, sir?
Make a system call.
To make a system call, right? We make a request to the operating system, and we say, hey, I want you to go and read this disk file. And the operating system turns that into a bunch of read requests to the device that it uses. device drivers you have in your system, and it collects the results, and then it responds to the system call. So if we think about the normal interaction between a user program and the operating system, that all kind of makes sense. Now, how does this work for virtualization? Well, it turns out that when you're in the processor, you have the same kind of thing going on. The processors no longer run where you just run your code willy-nilly and have access to everything. Otherwise, if we're on Clipper, then I can see your memory and you can see my memory. Why is that really not a good idea? Why don't I want you seeing my memory to either read or, more importantly, write it? How many people have gotten a null pointer exception? Be honest. Or a seg fault, your program just dies. All of that is because you don't know how to use pointers. Or you might know how to use pointers, but you may have made a mistake. Or you're using a library, and the person who wrote the library doesn't know how to use pointers, and they made a mistake. And they try to access a memory address that you don't really own. Well, if the system didn't protect me from you, then when your program runs with the wrong memory address, it's going to write values into my memory space. Well, my program is going to write stuff in your memory space. And so you wrote your bank account balance, and now it's a picture of my dog. Okay, bad things happen at that point. Imagine trying to debug that system. Well, that was the history of processors up through the Intel PC, way back when you guys weren't born yet, probably. The 286 even kind of did that. It allowed anything to run on anywhere. But with the 386, they started saying, you know what? We're going to carve off different parts of the processor, and you can't do things. So we can make it that you can't do I/O instructions, and you can't change the state of the processor. You can't write to the memory you don't have access to. And if you do, we're going to flag that as an error. We're going to make the operating system wake up and say, hey, operating system, this user program just did something really stupid. So either you fix it or kill it, but we're not letting this instruction go on. Makes sense, right? Well, all of the things that your operating system has to do has to talk to all those different devices. When I want to write images to the video card, I have to write to memory I don't own. The operating system does. And when I want to read from the disk file from my imaginary virtual disk machine, that has to read from a disk drive that I don't own. All of those become illegal instructions. And so every time I try to access a device, the processor says, dude, you can't do that. Operating system, fix this guy. Well, instead of saying this is an error, we're going to kill your program, VMware says, oh, no, I know how to handle that. This guy really tried to read from this file over here. Let me go read the data and give it back to this process. Oh, he tried to write to the video card. I know how to fix that. I'll write the data into that video card, the fake one, make it look real. So VMware very cleverly figured out how to interpret this stream of illegal requests and really stupid things and modifying memory that you don't have and turn it into what appears to be a real machine.
So is that why it runs a lot slower because it kind of acts as a new name?
Yes. Now, it used to be the case that these things ran terribly slow. But in comes transformative technology. Carol, you might know. When did Lisp start adding compilation modules? The 80s? Early 80s?
Yeah.
Somewhere in there. Sometime about 30 years ago, a little language called Lisp that we use in AI introduced the notion of being able to compile code. So you could type in your interpreted code, hit compile, and it would run much faster. And the guy who did Java, anybody know the man who invented Java? The language that you've been using since CS1? One of those pop quiz questions that they'll ask for an interview, and then you'll say, no, I don't know, and be really embarrassed. No one? Look it up. So the guy comes along and he says, well, this Lisp plugin is really good. We have the same problem in Java. Java is running all this virtual bytecode stuff, and we're trying to translate these Java bytecodes from this write once, run anywhere language to run on my processor or your processor, and it's really, really slow. So they invented this notion of hotspot technology that basically borrowed from Lisp. And the idea was that they would dynamically recompile your code. So whenever you start running a for loop under Java, instead of running it under bytecode, the hotspot compiler comes along and says, wait a second, we're going to run this thing 1,000,000 times. All right, stop, compile it to native assembly language, and run that instead. It runs a lot faster. Okay? So this notion of bytecode has made Java, and it's been in Java since like Java 1.4, and it's made Java much, 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 much faster. It used to only be on the really expensive server versions of Java, but now it's everywhere. So Java has this hotspot technology, and it's kind of transformed the way we use Java. Well, VMware, the people who did VMware, did the same thing. And this is really kind of the thing that really gets me excited about VMware's technology, because what they do is they take the stream of Intel assembly language instructions. Remember you did assembly language in 220? You had load, S0, 0, S4, add, S1, S2, S3, all those great instructions. The same thing is true under Intel, only there's more of them. But you take this stream of Intel assembly language instructions that have all these illegal instructions that we have to trap all over the place, and it just becomes nasty. What they do is they rewrite them dynamically. Now, what's hard about rewriting assembly language instructions? When you had like load S0, 0, S4, what was that 0, S4 doing? What was stored in S4 that we're loading from? So if you encountered this instruction, LD, put it into T0, remember that instruction? What does that do?
It's the offset of a memory address.
It's the offset plus the memory address. This guy says what memory address we're going to load from. Or better yet, branch. It's a loop, but loop was really not the word loop encoded in instruction, it was the address. All that kind of crazy assembly language stuff. Well, if VMware is going to rewrite your instruction stream and take instructions and make them multiple instructions so that they're no longer illegal, they have to know how to fix all of those memory addresses so that they don't break. I gotta give them some props for that, because that's not easy. I don't even know, and I'm a pretty smart guy. I have no idea how they do it and make it go quick. But they do. There's some very, very bright people who have figured that technology out. The really good paper that showed up in SIGOPS, if you just go on to the digital library, and if I think about it, I'll pull up the article. There's a really good paper written by the man who founded VMware. He was a Stanford professor, and one of his graduate students who worked with the technology with him, they wrote this paper that describes how they do this. And it was just fantastic. I mean, it's if you took computer org and you kind of understood most of computer org, you can follow the paper. They talk about all kinds of crazy things and how they made it work. Great stuff. All right, so we're back to our virtual machine. And at this point, we have our fully installed Ubuntu image. Oh, I made it user, not me. And let's look at that. Yay. So basically we now have a Ubuntu image, but it's not the pretty one like you guys have when you log on here. So I can install some new software, and you saw there that I had the ability to do sudo, which is the Ubuntu way of saying do this as root. If I want to download this over the campus internet connection, we'll be here all day. So ignore the magic here.